This video lecture is about the relational model for relational databases. The major source for this material is the textbook, chapters 2.1 through 2.4, and also the reference by date and colleague, chapter 2, in particular, the material on RelVar, because it is a useful concept. This lecture will describe a brief review of sets and relations. Elsewhere, I will provide some supplemental material on sets and relations, although you should really have learned that material prior to this course, and any review of that should be simply review and not new learning. We will also discuss tables as relations, rows as tuples within a relation, columns as attributes, and the concepts of primary key and foreign key, and finally what schema and schema diagrams are. Okay, the relational model. The relational model consists of tuples and relations. Tuples are elements within a relation. From this, you know, from set theory. Okay, keys, schema diagrams will be new concepts in the relational model. Okay. One other thing, this lecture will not describe the relational algebra. The relational algebra is not technically part of the relational model. It is a method for doing queries on a relational model, as is relational calculus and relational tuple calculus, or domain relational calculus, or tuple relational calculus, and other query languages. The relational algebra is the main one that is used underpinning SQL. Okay, so brief review. What is a relation? A relation is a mathematical object, R. It is a subset of the cross product of a number of sets. The number of sets determines how big the size of the tuples are. So let's suppose we have set 1 equals ABC, set 2 equals 1, 2, 3. Then the cross product, S1 cross S2 is the set of tuples A1, A2, A3, B1, B2, B3, and of course C1, C2, and C3. Okay, 2 comments. Again, quick review. The order of the elements in a set is not important. Order within this is irrelevant. It is relevant for performance reasons in a database, but order within a set is unimportant mathematically. However, order within a tuple is important. Okay. The tuple A2 is not the same as a tuple 2A. Okay. Now, ironically enough, while order within a set is not important, but order within a table will affect database performance, order within a tuple is important mathematically, but order within the columns of a database has some marginal impact on performance, but is generally not a major feature of the relational database. So that's kind of an amusing concept. Now this, as I described it, is the cross product of the set. But that isn't a relation. Any relation R, let's call it Ri, is a subset of the cross product. Now notice it's not a proper subset. It could include all of the elements, or it could include some of the elements. So for example, we could imagine a GPA system out of 3 that says an A is a 3, a B is a 2, and a C is a 1. Then that relation is a subset of S1 cross S2, and in particular it is the set A3, B2, and C1. Okay? So, that's a very quick review of relations. You should probably review them further if you haven't looked at them in a while. Okay. The set, each set can contain anything. Mathematicians often deal with numbers, but they can deal with anything. So we could have a set of customers in a store. So we've got Ahmed and Brenda and Charlie and Doug and Ethan and Fred. You can kind of figure out where those names came from. A, B, C, D, E, F. Okay. Could be anything. So, at a base level, sets are the domains of attributes. So customer names, salaries, birth dates, working hours. If we're talking about a business supply relationship, part numbers, whatever it is that happens to be part of what you're dealing with. So a table in a relational database is nothing more than the physical embodiment of a relation. So if we have this as our relation, we'll call this letter to GPA relation. Then as a relation, it would be, here's the letter, here's the GPA, A, B, C, 3, 2, 1. This will be our table within our database. Okay? And the creation of tables is something I will get to later. So, the specific relation it embodies is determined by the table's contents. In the reference by date, he refers to the table as a relvar, a relationship variable, a relation variable, because it can change. Okay? His terminology is not necessarily so widely used, although it is very precise. So it's helpful if you have confusion over the precision, but it's probably also worthwhile understanding the term relation as it's more broadly used. Okay? So the specific relation is embodied, is determined by the table contents. So this is our specific relation. Suppose we said, well, wait a sec, we don't want to have a GPA out of 3, we want to use the North American Standard GPA out of 4. It doesn't substantially change it. We have letter to GPA, and we have the letter, and we have the GPA, and we'll have an A is a 4, a B is a 3, a C is a 2, and we have to erase this bottom line because we've gone a bit too far, or we've cut it off too soon. D is typically a 1, and then F is typically 0. And then we might even say, you know what? An A plus is 4.3, an A minus is 3.7, and maybe we introduce a B plus and a B minus, etc. Putting them there is kind of annoying. It actually sort of messes up our table. And if we actually add contents to the table within a database, it won't typically place them there. What we would actually have is erase that line, move it down, we'd simply have extra rows. And this is where order of data in the set is not important. 4.3, A minus 3.7, B plus 3.3, B minus 2.7, C plus 2.3, and typically there isn't a C minus or anything below D and F. So the specific relation has changed. It was this little 3-element relation, and now it's a 9 or 10-element relation. Okay. But it's still a letter to GPA conversion. Okay. If you like to think mathematically, this is worth looking at. Just before we do that, if the contents of the table changes, the specific relation is not the same. But the relation name is the same. The relation attributes are the same. Okay? So, if we consider a mathematical relation, okay, xy over the set of all positive integers, such that y is x plus 1. Okay? We could actually write that as a set. I mean, don't sit down and write it because it'll take you an infinite amount of time because there's an infinite number of elements to this set. But the elements of the set are 1, 2, 2, 3, 3, 4, 4, 5, etc. Now, if you imagine removing this element from that set, you still have a relation. It's not the same relation. It's no longer the relation xy such that y is x plus 1. It's now something more like xy such that y is x plus 1 and x is not equal to 2. Okay? So the point I want you to think about, and this is an important point to understand, look at the material on RelVars in the reference to understand it, but also you can think about it this way. The data is the relation. Okay? The schema determines the form of the relation. The schema is equivalent to the cross product, except without the actual cross product calculation. It simply determines what the possible set of relations are. Okay? The actual relation is determined by the data in the database. Okay, rows and columns. Relations, or RelVars, are tables. A row in a table is a tuple in the relation. A column is a base set from which the relation is formed. And I'll talk about attributes in a minute. In practice, rows represent entities, relationships between entities, or occasionally relationships between relationships, but we won't deal with that until we come a lot later on entity relationship modeling. Columns represent the attributes of some entity. Okay, what are the attribute types? The set of allowed values for each attribute is the domain of the attribute. Okay, so let's take something more traditional. Employee. Okay, we'll have an employee relation. An employee has a name, an address, a phone number, maybe a department, okay, a salary, and maybe a manager. This is fine. Okay. When we say, look at it here, when we say the set of allowed values for each attribute is the domain of the attribute. So if we look at name, the domain for name is the set of all, I'm going to say legal, not in a law sense of the word, legal names in the sense of whatever you consider to be a legal name within your database. Okay. An address, the set of all addresses possible for your employees. Okay, that's what that is. So, for example, a name is typically, and if we're using standard notation, it's an alphabetic letter. Typically, it's a to Z. Okay, followed by A to Z, and I'm going to say one or more times. Okay. So, Fred satisfies that definition, okay? Capital F and then R-E-D, okay? And ing satisfies that definition, okay? This would mean you couldn't have an employee whose name is J621, okay? Now, you might say, well, what if I want to call my kid J621? And you can get into that argument, and that's fine. And let's say we say, okay, it's fine to have people whose names are J621, and you say that's okay too. But then the question is, so why would you want to restrict the name to be part of a domain? And the answer is error reduction. Okay. Very simply put, all data inside a database is put in by some data entry clerk. Okay, that's not as true as it used to be because of things like IoT, the Internet of Things. That will feed into databases. Okay. So if I get some sensor data that's reading a temperature, then fine, so not everything. But suppose you want to register for a credit card, you need to enter your name somewhere. Somebody, some person is going to type into some computer, okay, a name. And here's the thing, people make mistakes on data entry. They make mistakes all the time. So the purpose of having everything come from a domain is to try to avoid errors. Why might we have an error? Well, here's an example. Suppose I have, instead of name, I have first name, middle initial, and last name. Okay? And I enter this, and I think I'm entering the last name. Sorry, I think I'm entering the middle initial, but I've actually moved over to the last name point. So, for the sake of argument, let's assume my middle initial is A. So I'm Paul A. Ward. Okay? But you make a mistake and you type Paul and you have a blank here and you type A and you hit enter. This is the point at which it's very helpful for the database to be able to say, no, that's not a valid name. Now, there are issues with this. There's a guy in California by the name of Stephen O. And there are also, of course, many Vietnamese people with the last name Ng, many Chinese people with the last name Li. So it was frequently the case in the past that the domain for a database restricted a last name to be 3 or more characters. And that causes problems. Okay. Who knows? Maybe some people change their name to Lee to avoid this. I don't know. Okay. It's not a great solution. A better solution is to say, okay, the domain is bigger than we thought it was. But understand that the concept is to try to reduce errors. So also here, having an address, well, what's an address? Typically it's a street number and a street name and a city and a province and a postcode. Okay? So ensuring that all of those are there is important. Department. Maybe we have a set of departments that we know about. Okay? Have sales, we have HR, we have engineering, and, I don't know, procurement, people who do buying. Okay. So we have certain departments. We want to make sure that when we have data entry in here, that it is a valid department. When we enter the salary, we would like to make sure that it's a valid salary. So the purpose of domain is to make sure that we've got valid data. Okay. What else can we say about attributes? They are usually required to be atomic, which means they're indivisible. Okay. So something like name might be broken down into first name and last name. It might not. I'm not going to talk about that further. I'm just going to say they're usually required to be atomic, and we will discuss more on this later. There is a special value called null. This is not like a null pointer. Null technically does not mean missing information. It does, but it's frequently used for that purpose. It usually, it should mean unknown. Okay. It is frequently used to describe simply missing data, though. Okay. Use null values judiciously. In fact, good database design often, not always, but often says no nulls. You shouldn't have nulls. Again, I will describe more about this later, but if you find yourself needing lots of nulls in your data design, it's probably not a good design. We'll describe that when we talk about normalization. Okay, so what is a relation schema? Let's have different attributes, domains associated with those attributes. We can then define a relational schema as a set of attributes. Sorry, not a set of attributes, a list of attributes. Okay. The order matters somewhat. Okay. It will matter in terms of how the database is implemented. It will matter in terms of how the database performs. It is also the case that if we describe our schema as having a particular order, so if we say the relation is A1, A2, A3, then people will expect things to be in that order. If it's name, address, phone number, then if you do address, phone, name, then that's a problem. Okay. So the order in which things are listed matters in the schema. So here's a relational schema and an example, and this comes from the text. An instructor has an ID, a name, a department name, and a salary. Okay. Now, that's the schema, the relation schema. The relation R, conforming to that schema, is any subset of the cross product of the domains. Okay. So, let's say the possible IDs are some set of IDs, they're 6-digit numbers, say. Okay, and let's say the names are set of all possible names. And a department. The example in the text is a university department, so physics, ECE, ECE, music, etc. And I think the last one was salary. So whatever the salaries are, salary values. Okay. So one of the possible ones is 1, 2, 3, 4, 5, 6. Einstein, music, and $53. Okay, and another one is 1, 2, 3, 4, 5, 6. Einstein and ECE and $247. Okay, etc. And the reason you will have all of these possibilities is because what we have is the cross product. Okay. Now, the relation is going to be a subset of that. So Einstein isn't in music and Einstein isn't in ECE. It turns out that Einstein is in physics. Okay, so we'll have the actual remaining relation, tuple for the relevant relation for Einstein would be whatever his ID is in the physics department with whatever his salary is. That will be part of the relation, and that will be part of the relation because we will have this table, instructor with an ID and a name and a department and a salary, and we'll have some row containing Einstein specifying this information, okay? And that'll be that, okay? And this row is the surviving element, as it were, from the subset of the cross product, okay? So, an element T of R, and a tuple of the relation is a tuple, an n tuple, because it's got n elements in, and it corresponds to a row in the table. Okay. The order of the elements doesn't matter, sort of. Okay. It doesn't matter in a logical sense, although it will matter in terms of how operations are performed. Okay. So a relation instance, and again, if we go to the date book, he will refer to this as a relvar, okay? So he won't distinguish a relation instance. That's a relvar for him. But that's the concrete values of a relation, okay? If you will, that is the data in the set. So at a particular moment in time, there was a particular value for the relation schema, okay? One final comment, schema is also used to refer to all of the schema within a database. So suppose we have instructor as one schema, and we have department as another schema, etc., etc. We may refer to these collectively as the DB schema. Okay. We do not tend to distinguish between the particular instance not the instance, the particular one relation versus all of the relations in the set. We tend to use the word schema to cover them all. Okay, so here's an example of a relation instance. We've got an ID. Here's Einstein. Apparently it's 22222, not 1, 2, 3, 4, 5, 6, but whatever. So here's a tuple or a row within the relation instance, okay, these are the attributes, okay, the domain, these are apparently 5-digit numbers for this, okay, set of all names, set of all departments, and set of all possible salaries, so these all have their own domains. Okay. They're unordered. This is the same as this, okay. This one, I'm not sure what the order is. I don't think there's an order to this. No, not by salary. There's 95 and 92, not by department name. It looks pretty random, to be honest. Certainly not alphabetically by name, and certainly not by ID. Okay. Again, is irrelevant logically. Okay. For performance reasons, it will make a difference. You don't have much control over it, but we'll talk about that later in the course. Okay. A database comprises many relations. Okay, how many is many? Well, the example that they give through the ongoing university example is maybe a dozen relations. Okay, a dozen is not many. The smallest significant real database I've ever used has something like 32 different tables in, each of which has at least 10 and up to 30 columns per table. Okay. There is an organization called SAP, S-A-P. It's a German company. I'm not sure if they're owned by somebody now. I lose track of these things. But basically what they do is business process automation. Okay. So large businesses are run by business processes. For example, you want to hire a person, there's a process for that. If an employee has a baby, there's a process for that. If an employee wants to take vacation time, there's a process for that, etc. Okay. The last time I checked, so SAP creates what they consider to be an abstract business. Okay, you've actually run into a different one. Quest is built on top of a middleware. I can't remember the name of the company at the moment, but basically they create the notion of an abstract university. Okay. So, a university will give degrees, and they have students, and they have courses, etc. Okay. And so, if you want to take your university and start automating it, you will typically buy this middleware in order to get you up to speed much faster. So, this SAP had something on the order of 1,500 tables and relations the last I checked, okay? Whoops. So, not small, okay? So when this says many, don't think a dozen. Think thousands, okay? The examples in the text will be much, much smaller, okay? Yelp, I guess, has a small number of tables in their system that you'll need to create for assignment 1. It's less than 10, I think. But who knows whether they're omitting large quantities of information. I could easily imagine it, but that's a separate discussion. Okay, database designers may make questionable decisions which result in repetition of information or the need for null values. We will deal with this later in the course, okay? Suffice it to say, there are badly designed databases, There are databases that don't conform to normalization theory, but they're not necessarily badly designed. This is a complicated area. Okay, keys. If R is a relation schema, then K is a subset of R's attributes. Okay, so let's have relation schema R equals A, B, C, D. Okay. K is a subset of a, of the set A, B, C, D. So K could be A, B, C, D, it could be A, B, it could be B, C, D, etc. Okay, so there's on the order of 2 to the n attributes. 2 to the n possible keys. Okay, I'll let you work out the exact value. Okay. Okay. K initially is just some subset. K is a superkey if and only if the values of K are sufficient to identify a unique tuple of each possible relation in R. So, ID and ID name are both superkeys of instructor. Okay, let's go back a few slides. Okay. Are there overlapping salaries? Okay. 90, 95, 60, 75, 80, 72, 65, 62, 92, 40, 87, 80. I don't think there's any duplicates. Could salary be a superkey of the relation? And the answer to that question, no, because to be a superkey, it must be sufficient to identify a unique tuple of each possible relation. So if we go back here, if salary was specified as a superkey, then I can't hire Fred for whatever area at $80,000 because there's already someone with $80,000. I don't want that limitation. That would not be an acceptable or reasonable limitation. So even though salary happens to be unique here, it's not necessarily unique. The same thing for the name, okay? There are no duplicate names, but it is not necessarily the case that there would be, that I would want to be constrained. I have a Wu in finance. I don't want to be in a position where I can't hire a second person called Wu in finance, okay? So, I just said name isn't sufficient to be a superkey because we could hire someone with the same name. If it's not sufficient to be a superkey, why is ID and name a superkey? And the answer is because ID is a superkey. Let's go back here. I'm going to carefully pick the IDs such that they are unique. Okay, I'm going to make sure they're unique. So ID will be unique. Now, if ID is unique, then ID and name are both unique. Or ID and department number, or ID and anything is unique. So, whoops, not here. Here. Oops. ID is unique, therefore ID and name is also unique. ID and department is unique, ID and name and department are unique, ID and salary are unique. These are all super keys. So understand that there are a lot of potential super keys. Okay. What's a candidate key? A candidate key is any super key such that I cannot remove an attribute from the key and it is still a super key. Okay, so this example is not a good example for that purpose because ID is unique and there's nothing else that's unique. So let's think about something else. Name, street number, street name, city, postcode, SIN number, that's social insurance number. Whoops, I guess I don't need SIN number, that's redundant, it's SIN. Okay. Etc. Okay. Now let's think of name as, actually we'll make that, whoops, first name, middle initial, last name. Okay. And we'll have, say, employee ID. And date of birth and time of birth. Now here's something interesting. Two people can have the same date of birth and time of birth. Can two people have the same date of birth, time of birth, and location of birth? Well, if we get location of birth down to the level of room number, hospital name, then the quick answer is no. Even if we have two babies born at exactly the same time in exactly the same hospital, they're going to have different room numbers. Okay, so if we consider this relation, we've got things like social insurance number, that is unique. Okay, I'm going to change the colour. Unique. This is unique, the employee ID. Okay, but for the sake of argument, this combination is also unique. Now here's the thing. What are the candidate keys? This is a candidate key because social insurance number is unique. What that means is SIN plus name is a super key, and SIN plus city and SIN plus anything, these are all super keys. Okay, and we can remove everything from them except SIN, and SIN, the social insurance number, is unique. You can't remove that down to nothing because you wouldn't have anything. So this is a candidate key. Employee ID is a candidate key. And then we have a third candidate key, which is this, well, we have this third super key. Date of birth, time of birth, location of birth is a candidate key. Well, it's a super key. Is it a candidate key? Let's have a look at the requirement. No attribute can be removed and it is still a super key. Super key is a candidate key if it is minimal. Minimal means we can't take anything extra out of it. So, looking over here, we cannot take anything out of it. This has 3 attributes in. These each are 1 attribute. So, is this minimal? And the answer is yes, it is minimal. It has a different minimum, okay? It is equivalent to, suppose I draw a graph. Okay. Imagine I have some algorithm data structure type graph. Okay. And these are all the bottom. Okay. These are least elements in the graph. Actually, they're separately least elements, but so are these. Okay. Any one of them is least element within a graph. Okay. There is no element less than it. Okay. There's more than one. It's the same as this situation here. The fact that these are single attributes doesn't mean this multi-attribute collection is not a candidate key. It is a candidate key because you cannot remove any of the attributes from it and still uniquely identify the tuples. Okay, and again, remember, uniquely identify for any possible relation, not necessarily a relation within the set as it stands at the moment. Okay, one of the candidate keys is selected to be primary key. Which one? Why? I'm going to leave you to think about that. We can talk about it on Tuesday, tomorrow, in the Q&A. But think about how you might select a primary key and how you might justify that. Okay, finally, whoops, that should probably be blue. A foreign key constraint is an attribute value in one relation that must appear in another relation. So let's go back up here. We had this notion of a relation in which we had an employee who was a member of a department. Okay? One of the attributes was department. Well, let's think about that. Employee, name, department. Suppose we have another relation, department, which has some department identifier. This would probably be an identifier. Have a name. Maybe it has a building it's in. Maybe it has a budget. Whatever it has. Okay. We want to make sure that every employee, whatever department they're in, has to be a valid department. Okay. So the way to do that is to say, okay, any of the elements here, the domain of this, it comes from here. Okay. So this is referred to as a foreign key. Okay. This is the referencing relation, and this is the referenced relation. Okay. So, for a department ID to be valid here, it has to exist in this table. Okay. That's the simplest form of foreign key. A more complicated set of foreign key is a set of attribute values that must appear in another relation. Why would I have a set? Well, let me give you an example. Suppose I had an employee by name. Whoops, employee. Employee, and we have a first name and a last name and some other things. And suppose we have a reference elsewhere to some other relation, and I'm not going to try and come up with some nice notion. I'm just going to say relation. Okay. It is what it is. And this relation, for whatever reason, is using the first and last name of employees. Okay. It becomes critical that it is the pair here that references the pair here. Why? Well, let's think about this. Suppose we have Fred Jones and Mary Jane. If we had this references this, and this references this, then we could have Fred Jane and Mary Jones. But those aren't valid employees within the list. It is important that it is the pair that is referenced, because that way we can prevent things like this, because we say Fred Jane. Wait a minute, there is no Fred Jane in here. There's a Fred Jones and a Mary Jane, but there is no Fred Jane. So the combination of attributes, when it's warranted, is more restrictive than the individual. So please make sure you distinguish that, because it becomes very easy to make that mistake. Again, terminology, reference relation, referencing relation contains a foreign key. The reference relation contains the referenced key. That's frequently the primary key. It's not required. What is required is efficient lookup. Again, we will cover that later. So finally, just briefly, a schema diagram is a diagram that captures the entire schema, the collection of schemas, depending how you're using this word. But as I said, schema covers all of the relations as well as an individual one. A relational schema diagram illustrates primary keys, foreign keys, attributes, etc. So let's take an example. Here's the course. The relation name is course. The attributes are course ID, title, department name, and credit. The primary key in the relation is the one that is underlined. If there are multiple attributes that are required to be part of the primary key, they are collectively underlined. So this one has multiple attributes underlined. This one has multiple attributes. This one has multiple attributes. Okay. Sometimes it's all of the attributes, but not always. Okay, so relation name, relation attributes, primary key. The arrows are then the foreign key. So course ID is a foreign key to course ID in course. Prerequisite ID is also a foreign key to course ID. Okay? These ones. This is an unfortunate notation because it suggests that these are individually 4 separate foreign key relations to this. They would not be. This is a single FK over 4 attributes. Okay? This diagram form that's given in the textbook is poor for this reason. Okay? There is a better way of illustrating multi-attribute foreign keys, and I would like you to use it in this course. Let's say we have 3 attributes A, B, C that are collectively going to reference D, E, and F over here. The way to illustrate it is each one can have an individual line, but those lines should join together to form individual line, to form a single line, which then breaks apart into individual lines. This way of illustrating it means you will be clearly designating that that is a single foreign key over 3 relations, and that is distinct from 3 separate foreign keys, 1 for each. Okay. It is only because I happen to know that this setup has to be a single foreign key for this, because it's section ID, semester, and year. You do not want year to correspond to year. You don't want that to be a single foreign key, because basically you will have every year in here. It would be meaningless as a foreign key, for example. So it is the collection, okay? This, by contrast, these are distinct separate foreign keys. The course ID must be a valid course. The prerequisite must also be a valid course, okay? Now, in this particular case, we can determine that those are separate, but you can't always just by examination, and that's why it's important to get that right. That's it for this lecture. I hope to have additional material up in a little while, but that's good for now.